My name is Marina Durfey, and my summer research is studying randomly packed discrete domains for bonded particle modeling of isotropic solids. I would like to thank my sponsor, Sandia National Laboratories. I would also like to acknowledge my mentors, Sam Martin and Dr. Marcia Cooper of the Dynamic Material Response Lab at the Texas A&M Turbo Machinery Laboratory. Many materials exhibit isotropic elastic behavior and under severe stress states may also fracture. DEM is a great tool for simulating fracture, but also must perform well when predicting isotropic elastic material behavior. Bonded particle modeling uses a discrete element method, DEM, where particles that represent a coarse-grained volume of material are bonded together in a network to simulate continuum material behaviors. Randomly packed discrete particle elements are preferred over lattice-placed discrete particle elements for their improved geometrical isotropy. In the randomly packed discrete domains of this study, I'm investigating the relationship of the geometrical isotropy to the mechanical isotropy, which is relatively unexplored in the literature for bonded DEM simulations of solid materials. My research method starts by randomly packing particles in a large domain that is then compressed until the desired packing efficient is achieved. Once the domain has been created, a smaller virtual cube is extracted and each discrete particle in the cube is bonded within LAMPS. LAMPS is a DEM and molecular dynamic package developed by Sandia. Each extracted cube is then compressed along one set of opposing cube faces. After compression, Young's modulus and Poisson's ratio are calculated. In order to understand the relationship between the mechanical and geometric isotropy, the virtual cube is extracted in different orientations. This is done to maintain a nearly consistent arrangement of discrete particle elements while modifying the geometrical relationship between the bonded network and the virtual cube faces. The independent variables of this research are the virtual cube orientation and seed value to initiate the random particle packing process. The extracted cube is rotated in the theta and phi directions. The dependent variables of this research are the macroscale Young's modulus and Poisson's ratio calculated from each virtual cube. The applied stress, sigma m, is computed by summing the force applied to the top face and dividing it by the cross-sectional area. Young's modulus and Poisson's ratio are computed with the applied stress, sigma m, axial strain, epsilon z, and lateral strain, epsilon x. The controlled variables are domain size, microparameters of the bonds, and the particle coordination number, which determines the average bond length. For the project, I built 20 different large domains and extracted 31 virtual cubes with orientations varying in the theta and phi directions. This is a total of 620 simulations. The computing portion of this research has all been done using LAMPS version June 23rd, 2022 Update 2, as well as my local machine and on the Texas A&M High Performance Research Computing Cluster Grace. I'm also using Python scripts for automation. With each orientation of the cube, I've begun assessing the mechanical isotropy as shown in the plots. The graph to the left shows Young modulus as a function of the seed value for randomly packing the domain. The graph to the right shows the Young's modulus as a function of the virtual cube orientations. The spread in the data is associated with the 31 cube orientations for each seed value in the left plot and the seed values for each cube orientation in the right plot. Both graphs show there is a distribution of Young's modulus about similar mean values, with more variation of the means observed as a function of the cube's orientation and the plot on the right. I will continue to study the dataset further to characterize mechanical isotropy. My future work will continue to assess mechanical and geometric isotropy of randomly packed and bonded discrete domains. Mechanical isotropy is expected to be a function of geometrical isotropy. I plan to characterize geometric isotropy in terms of the distribution of the bond orientations. Once I characterize the critical aspects of the randomly packed domain for modeling isotropic material behavior, I plan to predict the behavior of a 3D slender beam under horizontal loading, uniform pole loads, and bending moments. This research is an extension of work done by REMI 2019, except not in a lattice-placed discrete domain. I hope you enjoyed my update on my research for studying randomly packed discrete domains for bonded particle modeling of isotropic solids. Thank you.